All right. So I think we're live again. Hello, everyone. Welcome back to another edition of Quarantine Thermo. Um, so this week we're very pleased to have Dr. Géraldine Haack of the University of Geneva, and I'm particularly grateful to Géraldine this week for stepping in at short notice. So thank you very much, Géraldine. That's really, really kind of you. So I guess many of you know Géraldine, but for those of you that don't, she's an expert in transport, mesoscopic physics, quantum information, quantum thermodynamics, and she's been doing some very interesting work about how to harvest entanglement from kind of thermal fluctuations. And so this week she's going to be telling us some new results from her work on autonomous entanglement engines. So before I hand over to Géraldine, I'll just explain the format to anyone who is kind of new to these talks. So basically, Géraldine will speak uninterrupted for however long she wants. And then at the end of the talk, we'll have questions. So if you have any questions during the talk or at the end, please just write them in the YouTube chat window and I'll relay them to Géraldine at the end. Okay, so without further ado, let's hand over to Géraldine. So please go ahead, Géraldine. You can share your screen.
Okay, so thank you, Mark, for this small introduction, and I'm really happy to be part of this series of talk, and I thank you and the group of John for this initiative. So let me share my screen and go to my talk. Okay, so today I would like to present new results on autonomous entanglement engines that we obtained with so my PhD student, Chiche Candelval, Nicola Palazzo, who was a master's student last summer in our group, and so Nicola Bruno, who is a professor in Geneva. So just to start and to introduce the topic, I would like to briefly recall a few specificities of thermal machines and how we can discuss quantum properties of thermal machines. So what is typically done now is like if you consider thermal resources for operating a thermal machine, to work in the quantum regime, you can consider a working substance which is made of nano constituents, and then you can try to exploit the quantum properties of this working substance to, for instance, increase the efficiency for various outputs, for instance, for producing work or for obtaining a cooling ratio, a cooling power, or for operating your device as a thermal diode to control the heat current. So there are various outputs which are the same as in classical thermal machines. So a few examples of quantum properties that you can exploit in your working substance are, for instance, the energy quantization. There was recently a talk in this series by Heiner Linke, so on a single energy level heat engine. You can exploit many body effects. This is also part of John Gould's group work. Or you can, for instance, also exploit quantum phase currents, for instance, in an interferometric setup. And there were various work by Peter Samuelson, Björn Sottman, Patrick Hofer, myself, Francesco Giasotto. So and that's only really few examples. Of course, here I don't mention all the possibilities you can exploit when considering like squeeze bath or so there are other quantum properties that you can exploit, but okay, when you consider only thermal resources, this is one thing you can do. And now I would like to emphasize another family of engines. So for people from the field, they have probably heard of them, and so they know a bit this type of picture, but I think it's nice to advertise that when working in the quantum regime, you can try to think differently. And how to think differently can be done in the following way. So still we consider thermal resources, so for instance a hot and a cold reservoirs, coupled to a quantum working substance, but here we will consider explicitly so artificial atoms, so qubits or like quantum systems in higher dimensions. And what you would like is not like a classical output like work, a cooling power or thermal diode or whatever, is to produce quantum correlations so between the individual constituents of your working substance. And this, you see it's then it will be, you can see this machine as a genuine quantum thermal machine because the output itself is quantum. So some nice features and interesting aspects of these machines are the fact that they belong to the big family of open quantum systems. So you have some dissipative dynamics through your working substance that you can investigate and exploit. You exploit, so the main idea is to exploit invariant thermal resources to create quantum correlations. And as I said, the output is quantum. So to really make clear that this type of family is a different family, so we introduced in our recent work the denomination of entanglement engines, reflecting the fact that there you use your input, so a heat current or thermal resources, to generate entanglement. So now that, so here, as you may guess, my talk will focus on this family of entanglement engines. So the outline will be as follows. So first, because the main goal is to create entanglement, I will briefly review the role of the environment when you want to create quantum correlations. Then I will present a very simple model and the working principle of such entanglement engine. And then I will present you new results. So for people from the community, I presented like last year also. I had a talk at the Quantum Thermo conference or at other places, but these are really new results where in fact we could derive a critical heat current that will ensure the creation of entanglement. So this could maybe be seen as an entanglement witness based on a heat current and could maybe provide an alternative to quantum tomography for assessing the quantum properties of the working substance. And finally, we also investigated the strong versus a weak inter-qubit coupling. And this was, I think, a long-lasting question when dealing with these engines, whether the interaction between the two qubits here, when it's large, what does it happen? Does it increase in a consequent way the amount of entanglement, or does it lead to something else? And here also we got some nice, interesting results. So that's the outline. So let me start by reviewing the role of environment. So in general, when you want to create quantum correlations, dissipation is detrimental. So you would like to isolate as much as possible your quantum system from the environment. And this is a very efficient way to generate quantum correlations, entanglement between two qubits. And this is, for instance, done by implementing the well-known two-qubit gates between artificial atoms, either superconducting qubits, as here in this picture, or NV centers, or trapped ions can be many, many different experimental platforms. So their dissipation is completely detrimental, so you don't use at all your environment, or you want to avoid as much as possible interaction with your environment. But then you can change your perspective, and you can say, okay, but I would like to exploit dissipation. And so then there are two, also well-known ways to exploit dissipation to create quantum correlations. The first one here on the left is to realize that in fact any entangled state is a ground state of a given Hamiltonian. So typically it's a complex Hamiltonian, and so to reach the ground state you will need to cool your system, so to cool your system to the ground state, so to use dissipation to a very cold environment. But here what's important is that it's an equilibrium setup. You just have a single environment that you want to exploit to cool down your system to its ground state. If you want to have an out of equilibrium situation, then what has been proposed in the last decade or 2 decades is also the possibility of engineering dissipation. So for instance, if you're able to tune the coupling to your environment or to engineer bass, for instance, to use a squeezed bass, this is known, or these techniques are known to be resources for creating quantum correlations. But of course, in that case, it requires lots of external control. So either you use time-dependent fields to control the coupling of your quantum system to the bass, or to engineer your bass. So it requires control. Now, why I recall that is because I would like to emphasize that when you think about a thermal machine, the idea which is behind, one of the main idea, is to use out of equilibrium situations, and you don't necessarily control the coupling to your environment in a time-dependent way, and so on. So it's the idea would be to come back to a setup where you use out of equilibrium bass, but without a time-dependent control on your couplings, neither an engineered bass. So let me present you one model and the working principle of an entanglement engine, how we can imagine it. So if I come back to this simple sketch, so I have my 2 resources, the hot bass, the cold bass, and I have individual artificial atoms between which I want to create quantum correlations. So first I model this. For instance, I can consider the simplest case, where my artificial atoms are 2 energy level system. So these are qubits. And of course, it does not come for free. So what I choose is that I coupled 1 qubit to the hot bass, I coupled the other one to the cold bass, and they are interacting. And here G is just the interaction strength. So formally, I can describe this system with its Hamiltonian. So I have my Hamiltonian of the system. Here, for the moment, I consider energy degenerate qubits. That's why I have a single energy E. And I consider a flip-flop interaction Hamiltonian, so which describes the interaction between the 0, 1 and 1, 0 states, where here I use the computational basis for the 2 qubits. So this is just the description. Now, few remarks. As you see here, it's a time-independent interaction Hamiltonian. So, and I will consider time-independent bass couplings. So from the thermodynamic point of view, there is no work and there is only heat which will be exchanged through the components of the setup. And so once you have this simple machine, you can, so there are different things you want to look at. So first is the quantum dynamics of this system. So here we focus on the steady state, but it's possible to also to look at the transient regimes. You can look at these dynamics depending on the coupling regimes. I will come to this point at the end of the talk. So for instance, you can investigate when G is large or when the coupling to the bass are large. And of course, large here, I mean large with respect to each other and with respect to the energy gap of the qubits. So that's the quantum dynamics, which is a topic in itself. And then you want to look at observables or properties of your working substance. And this can be done by looking at the heat flow or by looking at various measures of entanglement like concurrence or negativity. in order that you realize a bit, okay, the various progresses that have been made with these machines, let me recall maybe the first results we obtained in 2015 looking at this very simple setup. And this was done with Jonathan Borbrask in Copenhagen. So myself, Nicola, and Markus Huber in Vienna. And here, so we considered, in that work, we considered this simple setup. We looked at the steady state regime. We look at a weak inter-qubit interaction. So G is smaller or equal than the coupling to the bass. And all these couplings are much smaller than the energies of the qubits, such that, in fact, so then these assumptions are important for two things. First, then the master equation that you have to use is local. So it means that the jump operators in your dynamics will act directly on the states of your individual qubits. So, but okay, I don't want here to details. I will discuss that more a bit later. And what is important is that when G is much smaller than E, in fact, the ground state is separable. And why this is important, it's because in that case, you need an out of equilibrium situation to generate entanglement, because you see, having equilibrium with a single environment, you could cool down to the ground state, but the ground state is a separable state. So there is no hope to get quantum correlations if you have a single environment. So for this, we used a master equation based on a reset model, and we looked at the heat flow to the cold bath and the concurrence as a measure of entanglement. And what we obtained now in this work is that we had like a clear correspondence between the presence of a heat flow to the cold bath and the concurrence. So in order that you understand a bit the plots, let me explain you the axis and the quantities. So the concurrence, as I said, is a measure of entanglement. It takes the value 0 for qubits in a separable state, and it takes its maximal value 1 when the qubits are in a maximally entangled state or a Bell state. So you see that here the concurrence in the steady state regime differs clearly from 0 as a function of the hot temperature. And the two curves here are for various cold temperature. So if you focus on the blue one, which is for a cold bath at 0 temperature, then you see that as soon as you have a thermal gradient, you get a concurrence, a finite concurrence. And again, on the left, I show the heat flow to the cold bath, no? And there, as soon, if you look again at the blue curve, as soon as you have a thermal gradient, so TH is different from TC, which is equal to 0, you have a heat flow. And so whenever you have heat flow, then you have concurrence. And here these plots were obtained by maximizing over all other parameters of the model, namely the interaction strength between the two qubits G and the coupling to the bath. So there we had a clear indication that a heat current can sustain the creation of entanglement, the presence of entanglement in the steady state regime, and this will not be possible without these out of equilibrium situations. Of course, so this idea, of using out of equilibrium environments is not new. We were not the first one looking at this, and it was proposed before with various systems. So, for instance, two cavities coupled to a single atom, which are driven by incoherent light, or qubits subject to a noisy channel, or mechanical oscillators, and entanglement in all, or quantum correlations in all these setups. They do not come for free. In fact, you have to to choose a specific interaction Hamiltonian between the two entities you want to entangle, and this is done via a flip-flop type Hamiltonian like the one we considered, or the Ising type, or the XX type. So it depends. You have to choose a specific interaction Hamiltonian. And in our model, it was sufficiently, or it is sufficiently simple, such that we hope it's amenable for experiments, and either with superconducting qubits or with NV centers. So this is like we are discussing with groups, but it's a long-lasting. These are long-lasting discussions. So okay, so this work sets the important result that you can use thermal resources to generate quantum correlations. But this work also opened new questions, And the two main questions, well, two of the questions, let me say it like this, are the following. So first, if I come back to the plot of the concurrence, of course, the concurrence is non-zero. If again you look at the blue curve, it's non-zero as soon as you have a thermal gradient. So this is really nice. But you see that the maximal value is very small. It's 0.05. And I told you that its maximal value is 1 for maximally entangled states, which are like the ultimate goal if you want to use your state for quantum information processing. So this value is very small. And then the question was, but okay, can we design a new machine that could enhance, where we could get more entanglement in the steady state regime? And the other very important question, to my opinion, is like to really understand the fundamental relation between the presence of a heat flow and a finite concurrence, so a finite measure of entanglement. Like, how does heat current give rise to the presence of quantum correlations? And so, in fact, the first question, we looked at it with Armin Tavakoli and other people from Geneva, and Marcus Huber and Jonathan Brask also. And we proposed new types of entanglement engines, which we called heraldic, because we use some post-selection process. And with that, we could demonstrate that thermal resources are in principle enough to generate multipartite entanglement. For instance, these are results that I presented last year during some of the conferences. But so now what I would like to focus in the rest of this presentation is the results we obtained, which are related to the second question, namely the intricate link between the presence of a heat flow and so a heat current and a finite entanglement measure. And for me, these entanglement engines are of specific interest when you want to understand the intimate link between quantum thermodynamics and quantum info. Okay, so with that, I will start this part where we showed that it's possible to derive a critical heat current that will ensure a successful operation of the machine. And so what does it mean in that case, a successful operation of the entanglement engine? It means that for sure we know that the qubits are entangled if we have a heat current that is above this threshold set by the critical heat current. And so in that sense, it could be used maybe as an entanglement witness. Okay. So to make it clear, the differences also with respect to previous work, I took, well, that's the same slide I showed you about like the results we obtained in 2015, but I highlighted the differences. So in 2015, we looked at energy degenerate qubits, and here we consider the more general case where the two qubits are characterized by an energy gap epsilon 1, epsilon 2, and we even consider the possibility of having tunneling between the two energy levels, but I won't discuss that in this presentation, but we also looked at that case. Then, before we focused on the weak inter-qubit interaction, but now, so this will be the last part, now we also looked at a strong inter-qubit interaction. Previous results for demonstrating that bipartite and multipartite entanglement could be obtained within these engines were obtained with a reset master equation, which is a probabilistic evolution equation or a phenomenological master equation. Here we use the well-known Lindblad master equation. Also, both are equivalent. No, we focused on that. And for the quantities we investigated, it's here we explicitly look at the heat current and not the heat flow. So we really wanted to have this observable, the heat current through the system. And instead of looking at the concurrence as a measure of entanglement, we looked at the negativity. The only difference, such that you won't be lost when looking at the plot, is that the negativity, instead of, so of course it's a different criteria, but the negativity takes its maximal value, its maximal value, is 0.5 and not 1. But okay, I will come back to this. So, in fact, this is a scheme of this more general setup, where each qubit is characterized by its energy gap, epsilon H, epsilon C, H and C staying for hot and cold. Each one is also coupled to its bass, characterized by its temperature T hot and T cold. The coupling constants have gamma H and gamma C. And we allow for, so the interaction strength is G as before, but we allow for some detuning, which is the difference in energy between the energy gaps, which we call delta. So to derive the Lindblad master equation, you have to fix the Hamiltonians of each part of the system and then do some perturbative derivation to get the Lindblad master equation. So here, without entering into the details, it's the Hamiltonian of the system with so the energy gaps of each qubit. We have the interaction Hamiltonian written in terms of the raising and lowering matrices sigma plus sigma minus, but it's exactly the same interaction Hamiltonian as before, this flip-flop type interaction Hamiltonian. Here that's the Hamiltonian of the bass, so for the hot and the cold one. And here are the operators that can satisfy the commutation or anti-commutation relation, depending whether you consider bosonic or fermionic reservoirs. Both can be considered. And here that's the system bass interaction Hamiltonian, which follows a tunneling type interaction where you have, you see one excitation that can tunnel from the bass to the qubit or vice versa. And here are the raising or lowering operators for the qubit and the creation or annihilation operators for the bass. So this is just for giving you the definition. From there you can derive the master equation. If you assume a weak intercoupling strength between the two qubits, you get the local master equation. And what does it mean, the local? It means that, so this is a Lindbladian, this full line. Here you have the free evolution where you take into account the Hamiltonian of the two qubits and the interaction Hamiltonian. And here you have the dissipative part, where here these D are the dissipators, which are super operators. And why is it local? It's because the jump operators, which enters the dissipators, you see they will act on the individual Hilbert space of each qubit, because J here denotes the hot or the cold qubit. So each bass interacts locally with its own qubit. from this master equation, you can compute the steady state solution. The steady state solution is obtained by setting rho dot is equal to 0. And given the form of our interaction Hamiltonian, which is very simple, in fact, there are only 6 non-zero elements in the steady state density matrix. Well, it will be also 6 non-zero elements in the transient solution, but you have the 4 population and the 2 off-diagonal elements. And so what we achieved in this work is by deriving the steady state solution, we got an explicit expression for the currents, so the off-diagonal term, and for the heat current. And so this is what I would like to emphasize. So, they depend, of course, on the detuning, on chi is a complex is a complex expression that depends on all the rates, the G's, the detuning, and so on. But importantly, there is this factor, but it's proportional to gamma C, gamma H. So you see that, as expected, if one of the coupling strengths is 0, then there is no currents built. There is no currents in the steady state regime, and importantly, it's multiplied by the difference of either the Bose-Einstein-Bass distribution or the Fermi-Dirac-Bass distribution, depending whether you consider bosonic or fermionic Bass. And so here it's really the distribution of the hot Bass taken at the energy of the qubit coupled to the hot Bass, so it's epsilon h, and the temperature of the hot Bass, minus the distribution characterizing the cold Bass at the energy of the corresponding qubits. And for the heat currents, so we got also the exact expression. It's a prefactor with a complex expression, but again, as we would expect, it's proportional to the coupling rates to both Bass, and it's also proportional to this distribution. And for people familiar with transport properties, having the difference of Fermi-Dirac distributions of Bose-Einstein distributions that sets the observables, the current through the system, is very intuitive from, for instance, if you're familiar with a Landauer-Büttiker approach, but also from green functions, this difference between the distribution of the Bass sets the current that will flow through your system. But what is nice is that we showed that the currents, so the off-diagonal terms in the steady-state solution, also depends on this difference between the distributions. So this is an important analytical result because it tells you several things. So first, it tells you that C and the heat current depends in the same way on this distribution, And second, it tells you that at thermal equilibrium, if you will consider energy degenerate qubits, so epsilon h is equal to epsilon c, you will have no heat current and so no currents in the steady state regime. So this again shows that you need this out of equilibrium situation to get a finite currents in the steady state regime. So, that's one important result. Now, having a finite currents in the steady state regime is a necessary condition for having entanglement. You cannot have entangled qubits if all of diagonal terms in the density matrix are 0, but it's not a sufficient condition, And this is what the measures of entanglement quantify. So let me introduce the one we have been using, the negativity. The negativity of a density matrix 4 is defined as the sum of the absolute value of the eigenvalues lambda I of the -1. And these eigenvalues are the eigenvalues of the partial transpose of the density matrix with respect to one of the qubits. Okay, so that's negativity. And in fact, you can show that for a density matrix that has only these non-zero elements, there is only one eigenvalue of this partial transpose density matrix that can be negative. And so the criteria for having a non-zero negativity can be expressed in very simple terms, namely the squared of the absolute value of the currents must be larger than the product of the population for the doubly excited state and the ground state. So what is important is that if you satisfy this condition, then you will have a non-zero negativity, so you know that you have entanglement. And now you understand probably how we did to define a critical heat current. No? Before I showed you that we derive an exact relation between the steady state heat current and the currents C. And now we have a criteria for C to be sure that we have entanglement. And so this is what allowed us to define a critical heat current. So whenever the heat current is larger than this critical heat current, then we're sure that the qubits are entangled. And now we understand so all relations between a heat current and which is unobservable and the presence of entanglement. So let me illustrate these results with these two plots. So here I show you the ratio of the steady state heat current over this critical heat current. So according to what I told you, if it's above 1, I should have a finite negativity. And so below I showed you the negativity. Both quantities are plotted as a function of the hot temperature. The cold temperature was fixed and it was optimized for the various coupling rates. So, okay, before explaining the plots, also you see the blue curve corresponds to the 2 qubits being energy degenerate. So we work at resonance, whereas the dashed purple line corresponds to a finite detuning. So let us focus on the blue curve first. We see that as soon as TH is larger than TC, we get a heat current. And soon after, when increasing even more the hot temperature, this ratio goes above 1. And by looking at negativity, even if here, okay, it's very small, so that's why it's hard to see, but we have the analytical results, and we check numerically also that it's correct. We have the negativity starts to be non-zero. If we consider detuning between the qubits, so it's the purple line, dashed line, then we are off resonance, and this will in general also decrease the amount of entanglement that you can get, because you will get less heat current also. And so this is why, in fact, you need to have a larger temperature gradient to go above the threshold steady state heat current over the critical heat current. And then again, negativity starts to be non-zero. So here, fundamentally, now I think it's really clear what is the relation between the heat current and the presence of entanglement, which was not the case before. And second, I think this opens the way also to perform new measurements to certify the presence of entanglement, which could be an alternative to quantum tomography of the 2 qubits. So here, one will not need to reconstruct the density matrix of the 2 qubits to certify the presence of entanglement. But if one is able to measure the heat current, and it's above this critical heat current, then we can tell you that the qubits are entangled. Okay, so I see that, so I come to the last part of my talk. No, I don't want to be too long, but so so all the results I told you until now were derived in the case of a weak inter-qubit coupling, and we also looked at the strong inter-qubit coupling. So, and first, before starting, this result that we have this critical heat current is also valid in this strong coupling regime. So it does not depend on the coupling regime. But so it's important to realize when you deal with a strong inter-qubit interaction regime is that in fact, okay, one could naively think that you have the two qubits which interact more strongly. So naively you could think, okay, then I will get more entanglement. But what we have shown is that it's not so simple. And you have, in fact, to be very careful for the following reason. And this can be understood when you look at the total Hamiltonian of the two qubits, which is that one. And the reason is that if you have a strong inter-qubit coupling, and you will have only one environment at a given temperature T, then the corresponding thermal state can be entangled. This is, I briefly mentioned this at the beginning of my presentation, but there is a simple criteria to get entanglement at equilibrium when you consider a strong interaction between the two qubits. So this defines, you see, a range for the coupling and the temperature over which you can get entanglement. And it also makes the out of equilibrium situation less interesting. But okay, we really wanted to look at this in details. So we also looked at the dynamics using a global master equation. Global here, you see, in contrast to the previous master equation I showed you, then here the jump operators are acting, in fact, on the eigenvalues of the two qubit systems. So the eigenvalues are epsilon minus epsilon plus, and these are the corresponding eigenstates. So it's not anymore, these are not anymore operators acting onto states of the computational basis. So these are just technicalities. Here I just mentioned some of the recent work which have been looking at this global master equation. There was also the question whether one has to use local versus global, and this was discussed in several of the works. But so here, when we have an interaction strength G which is larger than the coupling to the bass, but okay, smaller or equal than E, then we have to use the global master equation. And this is what we got for the negativity. So this is a negativity as a function of G. The cold temperature was fixed and the hot temperature was optimized for each G. And the coupling to the hot bath was fixed, but the coupling to the cold bath was varied, and this gives the various curves. And here, just one message, is that in the global regime, so when you have a strong interaction, you get finite negativity, but in fact, this negativity is always upper bounded by the negativity that you get for the thermal state that I showed you before. Meaning that if in the strong interaction regime, in fact, the entanglement that you can obtain at equilibrium will be stronger than entanglement that you can get from this out of equilibrium situation. So the last plot that I would like to discuss with you is that one. Again, it's a negativity, but this time as a function of the hot temperature for various coupling strengths. So these are the blue, purple, and gold curves. And here it's an interesting plot to compare all regimes. So that's the thermal state in dashed line. and in the plane curves corresponds to the strong interaction regime. And you see the dashed line are always are always above the continuous line over a certain range of temperature, and this is because of this criteria that I presented you before. So, okay, then when you go away from this temperature range, you still get some negativity, but it's decreasing. But so that's one thing. And the other thing is that this dot dashed curve corresponds to the negativity that you will that one could get in the weak interaction regime. And you see that in fact the difference, there are not orders of magnitude of difference between the amount of entanglement that you can get in the local regime versus in the global regime. So, and the range of temperature in which you can work in the local regime is much larger than the range of temperature valid for a strong interaction regime. So these are few results that in fact shows the following things. So when you look at the strongly interacting qubit case, okay, you can also define a critical heat current, no? But you have to be very careful about thermal entanglement. In that case, you could get entanglement, and of course your critical heat current will vanish, no? So it does not provide you any meaningful information. In the strong interaction regime, you have a very high sensitivity to the hot temperature. So the thermal bias is, the temperature bias is much more, constitute really an issue if you think about experiments. It's always bounded by thermal entanglement. And so all this led us to the conclusion that if you consider if your goal is to generate quantum correlations from out of equilibrium situations to be in the paradigm of thermal machines, we believe there is in fact no clear advantage in having strongly interacting qubits. With that, I come to my conclusions. So I hope, in fact, with this talk, I could again emphasize the fundamental interest that you can find in looking at these engines. I think there are really nice setups to understand, as I said, so the relation between quantum thermodynamics and quantum information. The main new results was the derivation of a critical heat current, because we could understand so the exact relation between a heat current, so an observable, and the presence of quantum correlations. And finally, so we looked at this strong inter-qubit interaction regime. So as outlook now, there are many things. One can also look at these machines, but looking at at these machines when we engineer dissipation. So this relates to the first part of my talks, when you can exploit the environment in various ways. Then there is a question of the efficiency of these machines we are working on, and we are also discussing with many groups because it would be very nice to demonstrate this experimentally. So with that, I thank you for your attention.
Thanks very much, Géraldine. Lovely talk.
Thank
really
you,
clear. So we have lots of time for questions. We've also had lots of questions already, so loads of questions already asked during the talk.
Okay,
so,
great.
So I guess I'll just go through them. I mean, but some of these questions, of course, these were asked during the talk. So sort of, I guess some of the answers you sort of already alluded to or covered, but I think it's always nice to, repetition is always good, right? So I think I'm going to go. Sure, go ahead.
And what should I continue sharing my screen? Yes.
I think it's a good idea. Yeah, so yes. You can show your slides. Okay. Yeah. So Okay, so oh, and lots of claps and people saying thank you. So I should
Thank
relay
you.
that to you.
Thank you to all of you.
Okay, so Mauro Paternostro had the first question. So he asked, separable does not imply classical. Likely Geraldine will cover this later on, but is there any relation with weaker forms of quantum correlations?
Yeah, so in fact, that's a bit what I, briefly mentioned where I introduced now the measure of entanglement. We were looking at the negativity. And when I said that the presence of covariance in your steady state density matrix does not ensure entanglement, no?
Mm-hmm.
So you can look at, you could look at weaker form of entanglement. We showed that we have the exact expression of the off-diagonal terms of the density matrix. So if you want to look at other weaker form of quantum correlations, you could look at this. In our case, we focused on entanglement, maybe because it's, the form that is better known or like more attractive towards experiment. But if there are some interesting proposals for with weaker form, it could be an interesting point.
Okay, thank you very much. Okay, so the next question is from Junjie Liu. Actually, there were several kind of related questions on this point, but let me just ask Junjie's question first. So the question is, does the applicability of the Lindblad master equation impose a constraint on the ratio of epsilon h over epsilon c in the sense that this ratio could not take values far away
Yeah.
from 1? I mean, this was asked while you were still talking about the local master equation, but I guess it applies generally as a question,
Yeah,
right?
it applies generally, and well, in fact, you to be meaningful, no, you have to ensure that the detuning is also is smaller than the energy gap of the qubits. Otherwise, it does not mean something. It's losing a bit its meaning.
Mm-hmm.
But yes, you have to be so. The order of magnitude will be the coupling between the two qubits in the local version. The coupling between the two qubits, which are smaller or of the order of the coupling to the bath, which and at the same time, so epsilon and all these must be smaller, delta must be smaller than the energy gaps.
Okay, thanks. Yeah. And then I'm just going to skip ahead to a question simultaneously asked by Dura Segal and Gabriela De Chiara, which is kind of connected to this. So on slide 23, this was when you were talking about the current for the local master equation. Basically, both of them pointed out that you get a steady state current for equal temperatures if the energies are different from each other. So I guess they're both kind of asking for a comment on this.
Well, so, okay, in fact, you see, so let me, where is it, like here?
Here, yeah.
So indeed, even if you have the two baths being at the same temperature, because epsilon h is different from epsilon c, you have a finite heat current. And so at the beginning, we were indeed, we noticed that, and we were thinking, is there a mistake or not? But in fact, I think you can understand that it will be that the heat current is finite, but is very small, because in fact, you see, the coupling to the bath, they include for instance, if we consider bosonic baths, they include the Bose-Einstein distribution. No, the gamma plus is gamma c times NB, or the gamma minus is gamma c 1 plus NB. And so, in fact, if you see the energy of the qubits and the temperature enters this rate, and so even if you have two baths at the same temperature, these rates, due to the different energies, are non-zero. And so there will be, if you want, you have a finite probability to have a particle jumping in from one bath and jumping out to the other bath, but it's like very, very small. It's orders of magnitude. It's 10. We checked. Now I don't remember exactly the value, but it was like, it's much, much, much smaller than what you get when you have like out of equilibrium situation set by temperature.
I see. I mean, I guess my understanding, I guess people probably have different opinions on this, right? I mean, I guess I would have thought that somehow when you derive a local master equation, you're already making an assumption about the size of this detuning relative to the temperature. No? I mean, then basically this current that you get should be of higher order in delta over T than you actually take into account. I mean, do you know what I mean? I mean, at least that's one way that you can derive these local master equations can be derived in many ways, of course. So this is part of the
Yeah,
issue.
okay. Yeah, I see. Okay, I did not. Okay, I think we did not look exactly at this expansion in delta over T. But okay, that's when you derive the local master equation, as you said. If you assume that you are in the correct conditions to use that form of the master equation, no? I think you know anyway that the detuning is small, and then the physics about having a finite heat current even at equilibrium is really this very small probability because the rates depend on the distribution, which depend itself on the energy of the qubits.
Okay, thank you very much. So hopefully that answers both Vera's and Gabriele's question. Okay, so let me now skip back to previous question asked by Taufik Murtado. Is there a maximum bound on the amount of entanglement generated with this engine? Can it generate a Bell state?
Yeah, so okay, so that's exactly in fact what we are looking at right now with Shishir. So to give you an answer, so you see, to produce these plots, no, we have optimized over many parameters, and this was also the case in the work I did with Jonathan, Marcus, and Nicola in 2015. So there we also optimized over all parameters. And so one thing is that we are sure, no, that it's not possible to achieve a Bell state with this configuration. And this is why with Armin and my colleagues, we also work at heralded entanglement engine. And there we showed that if you have the ideal situation of a bath at infinite temperature and the cold bath at 0 temperature, there you have a finite probability to generate Bell state. So this is one part of the question. So, and then respect to the upper bound, that's what we are looking at, in fact, to characterize the efficiency of these engines.
Yes. Okay, thank you. All right, so next question was from Adrian De Volder, who asked, what would be the impact of non-Markovianity? Could we improve the entanglement generation?
Yeah. So, okay, that I think what I mentioned as an outlook, I think it's an interesting point. No, what happens if you consider this machine, but you engineer dissipation? No, so you put some time-dependent rates, or you put the spectral distribution of your bath that will lead to some non-Markovian dynamics, and then I believe that if you engineer correctly your bath and your rates, yes, I would say you can probably increase the amount of entanglement you get. Then you have to realize that you go a bit outside of the paradigm of using just incurrent thermal resources, but it will be interesting to determine whether when you engineer dissipation, how the efficiency or what the entanglement that you create, whether it's comparable to what you can do by implementing unitary operations between the two qubits. I'm pretty sure it can be less, but it's probably less, but it would be nice to determine exactly how it behaves.
Yes. Okay, yes. Thank you. All right, so next question is from Alberto Imperato, who asked, is there a generalization of the negativity to the case of multipartite systems, i.e. more than 2 qubits?
In fact, as soon as you want to quantify entanglement for more than 2 qubits, it's complex, and then you have different measures or criteria, and so no, the negativity, it's valid. It's a measure of entanglement which is valid only for 2 qubits.
Okay.
Yes.
Okay, thanks. And then, so Devera asked another question, which I think you kind of partially answered, but I want to just ask you again, because again, repetition is always good. So Devera asked a general question: do you observe suppression of entanglement with increasing temperature difference? So this was before you showed the global master equation plots. I mean, and then she said, okay, so I guess the answer is suppression of entanglement shows at strong coupling, right? So obviously, there a temperature difference doesn't help you. But I was wondering for weak coupling. Do you see what I mean? So I mean,
yeah. So for the weak coupling, it's the same. When you increase a lot, the temperature difference at some point it decreases.
I see. Okay, very interesting.
Yes.
Yeah, so you do see that as well in the weak coupling case.
Yeah. It's just that, in fact, the temperature range over which this machine works in the weak interaction regime is much larger than for the stronger interaction regimes. And that's, well, one of the arguments I see towards working, well, towards not working in a strongly interacting regime, no. And because of this thermal entanglement, well, it depends what you want to demonstrate, no. If you want to demonstrate a larger amount of entanglement, maybe you can optimize the stronger interaction case. If you want to demonstrate the functioning of an engine to generate quantum correlations, I would rather remain in the weakly interaction regime.
Okay, thanks very much. Well, okay, there was a question from, well, there's a question that was retracted, but I'm going to ask it anyway because I want to know the answer. So basically, have you thought about what happens when you add sort of time-dependent driving? I mean, is this something that you've considered? Would it be possible to go above the thermal entanglement kind of bound if you include some time dependence? Or I know it goes completely outside of the paradigm of autonomous engines.
No, but okay, so I don't have the answer, no, but again, I can refer to this outlook when you engineer dissipation, no? Yeah, I think it completely fits into that direction. And I hope, in fact, I would like to trigger interest among different people. So if people want to jump into that topic and look at those questions, I will be more than happy.
Okay, great. Cool. All right, so more questions still. So we have a question from Karen Hovyanishan. Sorry for butchering your name there, Karen. So Karen asks, have you looked into higher dimensional systems? Does the dimensionality maybe help with getting more negativity?
Yeah, okay, so in fact, okay, here I don't have the slides, but I will refer to these two works, no? And I also, so these are works I presented, no, in the past years. But so, in fact, the principle, if you want, the principle of an heralded entanglement engine is that if you want to generate strong entanglement between 2 qubits, in fact, you work initially with 2 qubits. You use the same principle out of equilibrium steady state. So the 2 qubits, so 3 levels now, are weakly entangled. There is nothing magic. But then the idea is that you project your 2 qubits onto a 2 qubit subspace. So you reduce the total Hilbert space, the size. And then we could show that, in fact, the amount of entanglement is much larger. And we can, but then you see it's a probabilistic process. So you have a certain probability to be in the desired 2 qubit subspace. And so, in fact, by increasing the amount of entanglement, you decrease the probability of reaching that state. So achieving Bell state is possible, but with probability 0. But achieving, in fact, states which violate Bell inequalities is possible, for instance, with a probability of 12%. And so we did it carefully. So for 2 qubits to be projected onto a 2 qubit subspace, and we generalized that to 2D dimensional systems. So there was, we did two generalizations, no? The bipartite case with n-dimensional systems, and the multipartite case where we considered only qubits, but we considered n entities, n qubits.
Okay.
So yeah, this we definitely looked at this, and this was done in these two works, and I think the results are well, it's more formal, no, but it really answers Karen's question.
Okay, thanks very much. Okay, and I think, okay, one more question. I think this is probably going to be the last question unless anyone wants to write in something quickly. So Archak Pukayasta from our group has a question. So he says, hi, Geraldine, thanks for the nice talk. I presume most of these are mixed entangled states. Is it possible to generate almost pure entangled states like this? And did you look at the purity?
Yeah, so again, thanks, Archak. We looked at this in these two for the evolved entanglement engine. And we could show that with a certain probability, but in some ideal situation, we could achieve, well, for instance, a singlet state, no? But in general, yes, indeed, in the setup I showed you, it's a mixed entangled state, so the purity is not one, yes.
Okay, thanks very much. All right, so that's lots of questions, so I think it's probably a good moment to conclude. So yeah, thanks everyone once again for tuning in, and especially thanks Dr. Géraldine Haack for such an illuminating talk, and especially thanks a lot again, Géraldine, for agreeing to step in. It was I'm really glad that you were able to do it.
Okay, thank you very much, well, all of you for listening to this talk, and thank you, Mark, again for organizing this nice series.